Welcome back to First at 4. I'm meteorologist Jacob Morse here on the road at the National Weather Service in Bismarck, taking a deep dive into how weather balloons are launched and the very useful applications of the data that they collect. Last week we showed you how the balloons are prepared to be launched, and now we have our latex balloon inflated with hydrogen with the parachute attached to a string 6 feet below that. 75 feet farther down is the radiosonde, which is the instrument that measures temperature, dew point, and GPS coordinates as the balloon travels about 20 miles up in our atmosphere. Weather balloons are launched twice per day at hundreds of locations around the world, including by 68 weather forecast offices across the contiguous U.S., allowing meteorologists to get a snapshot of the current condition of our atmosphere.
It's more of kind of like a temperature measurement that you would see from your normal thermometer, but aloft. And it also measures, like I said, humidity, and it measures, pressure and all that kind of stuff. So we were able to kind of build a bigger 3D picture of what is happening real time.
We're launching this weather balloon at 6 p.m. so that the data has enough time to be ingested into the next update of our weather forecast models. The balloon needs to be launched at these specific times, even in high winds or in a blizzard.
There are times where we have launched in 50, 60 mile an hour winds, so it is pretty brutal. So the only conditions it would be if we couldn't launch a weather balloon would be in a thunderstorm. We generally try to avoid launching in thunderstorms just due to the lightning issue and you having a hydrogen balloon, but also the fact that if you launch the balloon in the thunderstorm, it could corrupt your data as well with the updraft, so you're not getting proper representation of the atmosphere. It's kind of skewed based off of the thunderstorm.
One final thing needs to be done before the launch.
We have to call the Bismarck Tower to make sure that we are cleared to launch the balloon because we are close to the airport and we don't want to interfere with any international flights. So they have to give us an okay for us to launch the balloon. So what I do is I walk out far enough away from the building where it's not going to interfere with the balloon, and then we kind of just let it go.
Now that we have a successful launch, the balloon will rapidly travel up, with the first 25,000 feet or 20 minutes of the flight being the most important, since this is where most of our weather happens. However, the balloon will continue to travel into the stratosphere before popping once the balloon reaches about 25 feet wide. The balloon can also drift for more than 125 miles from the release point, depending on the prevailing winds aloft. However, in calm winds, weather balloons can stay pretty close to their launch point. Once the balloon bursts, the radiosonde returns to Earth via the parachute, and radiosondes can be sent back to the National Weather Service by mail.
I think they said about 10% get returned to maybe 5%, so most of them end up in people's fields, or they're all biodegradable, so even the parachute, everything will eventually break down, and it's good for the environment. But it's just more of kind of a launch and forget system, just based off of cost. It'd be hard to retrieve all of these.
Back inside, we can start to see our data coming in from the balloon.
So this right here is our SKU-T. We have our temperature profile right here, followed with our dew point, and that's kind of how we see the stability of the atmosphere, and we're kind of able to plot and track and see if the environment is stable or unstable.
This is the completed SKU-T diagram from our launch on May 21st, with temperature in red and dew point in green from the surface to tens of thousands of feet up. The temperature lines, which I've highlighted in black, are slanted, and other lines on the chart help meteorologists to judge how quickly temperatures are changing vertically in our atmosphere. When the lines are closer together, there's more moisture in that layer of the atmosphere, allowing for clouds to form there. Most of the balloon's flight is below freezing, as shown with the area shaded in light blue. Temperatures normally decrease with height in our atmosphere, but when the temperature line moves to the right on our chart, this indicates temperatures are increasing with height, called an inversion, which is a stable layer of the atmosphere. Wind speed and direction data is derived from the GPS coordinates of the radiosonde, and these are plotted as well as the balloon ascends. These SKU-T charts are invaluable for meteorologists, especially when assessing if conditions are favorable for severe weather. That's why these weather balloons need to be launched twice per day, 365 days of the year, to get accurate data of what's actually happening thousands of feet above our heads. There's so many things that we could do with weather radar. There's so many capabilities that it has, and we've been upgrading it over the years to give it more capabilities to help us warn for severe weather specifically. So last week we talked about velocity mode on radar and how that can allow us to see inside of storms, to see the speed and direction that precipitation is moving in. So for example, with severe weather, we could see that there's rotation within storms to detect tornadoes as well as damaging straight line winds. Usually when you load up your radar app, you could see the reflectivity mode, which just gives us the information about how heavy the precipitation is in a certain area. But there's also other types of products. We'll follow that waveguide back inside the radar, and inside the radar, that waveguide that brings up the radio frequency energy actually splits into two at the radar dish. So inside the radar, the waveguide is in two separate parts. And as the signal is being transmitted out from the radar, it goes in both the horizontal and the vertical directions. And that's what's called dual polarization radar technology. So the radar sends out horizontal pulses and vertical pulses. And what that allows is us to see the size, the shape, and the variety of different particles in the atmosphere. So you have your radio frequency energy that looks like sine waves in the horizontal direction. And with our dual polarization radar technology, we can send it out not only in the horizontal direction, but also in the vertical direction. That allows us to see the size and shapes of, for example, raindrops and hailstones. And the reason why that is important is because we can detect all the different types of precipitation that is falling, as well as seeing where there could be further intensification within supercell thunderstorms. So the reason why this is important is because you have different shapes and sizes of raindrops, hailstones are different sizes, snowflakes are different sizes, and we could also tell if there's non-hydrometeors, non-precipitation types in the atmosphere as well. So raindrops can be a bunch of different sizes. Once you get into the really big raindrops, that's where it looks like hamburgers because of the wind speeds as the raindrops are falling down to the ground. And obviously hail can be in different sizes with spikes or smooth hail, round hail stones as well. So one of the dual polarization products is called differential reflectivity. What this allows us to do is compare the vertical scale and the horizontal scale of the particles. So this is an example from 2021 in Morton County. You can see that on this section of the radar, we are detecting large hail because of the very low differential reflectivity values. We were able to see that behind the scenes and then warn that supercell for baseball-sized hail. On our normal reflectivity mode, there was also a hail spike. What that means is that we can see the hail attenuating the radar in a way that gives us another indication there's very large hail within that strong thunderstorm. The second dual polarization product I want to mention was correlation coefficient. That allows us to see inside the storm detecting how similar or dissimilar particles are. In this case, this was in Rolette and Towner County in 2016 when there was an EF2 tornado, and this was seeing where we were lofting debris. That is dissimilar, so any debris that is being lofted by a tornado is dissimilar from the surrounding precipitation. So it's a really powerful product, and in the wintertime, we could also see where there's rain versus snow and how that's delineated between the two. So I'm going to send it over to Chauncey Schultz, and he's going to explain how that new technology has really helped us with especially severe weather.
So we added that new dual polarization technology in 2012. So it's relatively recent, considering that the radar itself is going on about 30 years old, or just about 30 years now. The dual polarization in the last decade or so has really helped us to better detect different kinds of rain and snow, the precipitation types. And it's really helped us detect hail a lot better than we did historically, because we can tell if it's small hail, if it's extra large hail now. That really helps us with our warnings. One other thing that we can detect is actually debris. So thankfully, we haven't observed that from our radar very often, but if a tornado does damage, the debris field, so all sort of structures and things like that as it gets lofted by a tornado, actually gives a different type of signal as well. The dual polarization technology lets us parse that out from regular rain and hail in a big damaging supercell thunderstorm, so we can actually detect if a tornado is causing damage from the radar, if it's close enough to the radar, which we never historically could do before we had dual polarization.
So it might look like a bucket of spilled paint to some people on radar, but meteorologists behind the scene, we look at those products to give more insight as to what's happening, especially with these strong thunderstorms, using that dual polarization technology. This one's going to be about the limitations of radar, because even though they're very advanced machines that have been upgraded over the years, there are still some limitations and some precipitation that we can't see because of certain obstructions or distances from radar. So a reminder that the radar beam increases in elevation as it goes out from the radar. So the farther away you are from the radar site, the higher in the atmosphere the radar is sampling. And the way that we can look at that is, if you remember a couple weeks ago we talked about the volume coverage patterns. When there's no precipitation in the area, we just use clear air mode. What that means is the radar scans only a few elevation angles up in the atmosphere, and again the beam goes up in elevation as you go away from the radar site. When there's precipitation in the area, specifically thunderstorms, we go at a lot more different elevation angles, much higher up in the atmosphere, sampling those tall thunderstorms. But still, the farther away you are from the radar site, the less data that we can get because the radar beam increases in elevation. Another kind of downfall of radars is that you can't see precipitation directly above it. What that's called is the cone of silence. So at the Bismarck radar, the Minot radar, precipitation directly above the radar site we can't see because the radar beams go out at an angle. Now, with our coverage of Weather Service radars across the country, we have a pretty good network to see what precipitation is happening, but there are some notable gaps. In Bismarck and Minot, those radars can really see precipitation well over central and eastern North Dakota, but western North Dakota gets left out a little bit because the radar beam is a lot higher up. So here's some of the notable gaps in radar coverage across the country. Some of them are in more populated areas such as Charlotte, North Carolina, Harrisburg, Pennsylvania, and more in Tornado Alley down south where that's a little bit more problematic. In North Dakota, as I mentioned, far western North Dakota, the radar beam is more than 10,000 feet above the ground. So that doesn't mean there's no radar coverage in far western North Dakota. It just means it's a little bit harder to see the precipitation and detect low-level features such as snowfall or rotation within thunderstorms. But there is something that the Minot radar has done recently in order to try to combat that.
So the Minot radar is one of the only radars in the country that actually scans at an elevation below 0.5. So thanks to research that was done within the last couple of years, we lowered the angle of the Minot radar to 0.3 to try and gather more information at a lower altitude over western North Dakota to help with the detection of weather that's important to the western part of the state. It might not seem like that much of a difference, but it is when you start talking about elevation angles further and further from the radar as the Earth curves.
So that base reflectivity angle that most radars use, 0.5 degrees above zero, is useful for most locations, but with the much more limited coverage in western North Dakota, having that 0.3 degree elevation angle is really useful. In 2018, there was a tornado that came through Watford City, and unfortunately there was a death attributed with that tornado, but that goes to show that sometimes there could be some gaps in the radar coverage in the far western part of the state, and we need further radars, more data in those areas to get low-level information with either severe thunderstorms or in the wintertime with detecting snowfall that might be falling in that area. So what there is with the Department of Water Resources, they have a radar in Bowman as well as in Stanley, and those radars can help to detect precipitation in far western North Dakota. They're a little bit of a lower power radar, and actually are radars that the National Weather Service used to use. They're now just repurposed in, again, Bowman and Stanley. So here are some of the useful applications of those radars for western North Dakota residents.
Well, the purpose of the radars originally was to, and still is, to support the cloud seeding program in western North Dakota that is conducted every summer during June, July, and August. So that was the original intent of getting the radars deployed to help in that effort. As far as the radar gaps in western North Dakota go, we've been operating the Bowman radar year-round since 2011 to help fill a gap in coverage in the National Weather Service radar network. That's been a nice bonus for the citizens that live in those areas. In the wintertime, especially when precipitation, the clouds that produce it are lower. They're not as high as thunderstorms in the summer. We need a radar that can fill in a gap and can do a better job of detecting the precipitation that's lower to the ground. I think it is unique, and I've had some conversations with some colleagues of mine in some of the other Western states, and this actually was discussion. This was a genesis of some work that was going on and is going on currently in Colorado to help fill some gaps in radar coverage there too, in the mountainous western part of the state where they had significant gaps in coverage. So I think things like this can be very helpful to filling in these coverage gaps in the National Weather Service system.